Okay, so welcome back to the second half of Information Theory Lecture 10. In this lecture, or this half of the lecture, we're going to actually be discussing Shannon, Fano, and Elias coding. And it's another form of symbol code in the same sense as either the Shannon code we saw before or the Halfopen code, in that what we're going to be doing is essentially sending one bit string per source symbol at a time. But this one actually derives its code words in a way that's very, very different than what we've done so far. But it's also something that's going to be very, very reminiscent of what ultimately is going to be a stream code. And so we want to cover it this section first, because this will be a pretty critical section, pretty thing to understand for arithmetic coding. So what we're going to do in this type of coding is we're going to, in some sense, use the cumulative probability distribution to compute the bits of the code word itself. So in other words, we're going to essentially use the numeric value of this cumulative distribution in binary. Probability was equal to 0, we could essentially just remove that symbol from the source alphabet, because it would, if it has probability 0, never occur. So all probabilities are strictly positive, and we need that assumption in a number of instances in order for any of the stuff that we talk about to be valid. So the first thing we're going to do this is for, x in the set 1, 2 through n. Basically, we talk about this stuff. All the rest of that, but and so what this essentially looks like is obvious, right? But this is the reason why I'm going through this so carefully, as you'll see in a minute. So basically, at each point, at each next integer, sort of this is open at this point and closed at this point. It jumps up to the next value and it stays there until that. So what's happening there? So now what we're going to do is define f bar of x, which is basically summing up everything up until x, before it was a less than 2 x, now it's a less than x, and then we're taking the last guy that only half of it. So another way you can write this is f of x minus 1 is p of x. And so the black curves are f of x, and so it's the thing that we saw before, the black curve. The one we're just defining is f bar of x. And so what this does is essentially it starts at half of p of 1, and then goes up by when we get to 2, it goes up by p of 1, goes up to p1 plus half of p of 2, and so on and so forth. And you can see essentially that these blue little lollipops, or whatever you want to call them, lie halfway between the white and the black ones. So zooming in a little bit, this blue thing lies halfway between this black and this white. Okay, that's how we're doing f bar. And so basically, in fact, f bar is a point between the white and the black, and f bar is a point between f of x minus 1, which is the white thing, and f of x. And the reason for that is because we're, again, assuming that p of x is strictly greater than 0. So we start out with right away we have this. Now the important thing to note about this equation is the strictness of this. Note that this is strict here, and this is strict here. So f bar is strictly between these two values. Okay. Now again, since p of x is always greater than 0, when a is not equal to b, we have that f of a is not equal to f of b, right? So then in some sense, that also means, well, it's identical to f bar of a not being equal to f bar of b. And why is that? Again, for the same reasons, because a is not equal to b, and because p of x is greater than 0 strictly. And so what that means then is that we can use f bar of a as a non-singular code for x. So remember, f bar, all these guys are essentially numbers between 0 and 1, and we can expand that out in binary, and then everything after the binary point becomes a binary code. And this is the condition that's necessary for non-singularity of a code, and so we could use the binary expansion of f bar of a as a code for a. This should read a here. Okay. You can get that from looking at the countably infinite craft inequality. Now this is going to be uniquely decodable code, and the reason is because of the uniqueness property, because basically for every a not equal to b, we're going to have a unique code. But the problem with this code is that it's long, that some code words can potentially be an infinite length. I mean, there's nothing that has restricted the probability distributions to be rational, let alone dyadic. I mean, these things could be irrational, they could be any value. What we do then in order to make it a non-infinite length is we truncate f bar to L of x bits. And we notate this in this way. So it's sort of like the floor notation, but truncated to L of x bits after the binary point. And I'll explain what that means. So let's, for example, say that L is equal to 4. And let's say that f bar of x happened to be this very, very long binary expansion. And let's say it goes on forever. If we truncate it to 4 bits, then we just get 0.0110. So there's 4 bits after the binary point here. Okay. Now the question is, we want to make, how much do we truncate? I mean, we want to truncate this so that it's not infinite. And of course, obviously, any truncation would make it non-infinite. Any finite truncation would make it non-infinite. But we also want to truncate it so that it's still uniquely decodable. But then on the other hand, so we don't want to truncate too much, but we don't want to truncate it too little either. We want to do the most amount of truncating without losing the unique decodability of the potential coboards. And so the question is, how long should the lengths be in order to retain unique decodability? Well, let's consider equation 10.21, where we see that any of the original values of f bar minus the truncated value is going to be less than 2 to the negative L. And you can kind of see this as in the following way. Like we've got, let's say that here's a particular binary value, which I'm just writing it as a bunch of x's here. And then here's the truncation to 4 values. And when we do this subtraction, we're going to get this. All these guys, all the x's are going to cancel out, and all this stuff is going to be retained from here. And we're going to be left with something which is certainly no greater than 2 to the negative L, which is in this case is 0.0001. This is 2 to the negative 4 in this case, because in this case it's obvious. This is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and 2 to the negative 4. Okay. So now, if we choose, for example, L to be the Shannon lengths, so that's basically the information sealed and added 1, which is essentially the Shannon lengths plus 1. Then if we look at 2 to the negative L, that's 1/2 times 2 to the negative seal of the log of 1 over p. And the reason, so basically the plus 1 here becomes this 1/2 out in front. And what we're left with is 2 to the negative seal. Okay. And that's going to be less than this, because basically we're getting rid of the seal function, which can only slightly decrease it, which is going to increase to the negative of that thing. So it's going to be slightly bigger, but now we can actually get rid of the 2's and the logs, and what we end up with is just p of x over 2. So that's basically the value, and that happens to be equal to, but just by definition, f bar of x minus f of x minus 1. remember f of x minus 1, to get f bar of x, we just add on p of x over 2. Okay, so what this then gives is the following. When we take these two equations, so we start with, we have this right here, which is equation 10.21. And then we combine that with the thing that we just showed here, and we get the following results, that 1 over 2 to the L is less than this strictly, and it's greater than this strictly. Now again, it's important to realize that these are strict inequalities. They're not less than or equal to, these are less. And so now what we can do is solve for a lower bound for the truncated version, which basically says that the truncated f bar to L bits is going to be strictly greater than f of x minus 1. Now, so this strictness is good for the following reason. I think I've got a picture here. So here's basically the picture. We have that f bar of x, which comes from equation 10.26, we have this guy, which says that the truncated f bar of x is going to be greater than f of x minus 1, which is this part here. And then since it's a truncated f bar, we have this, and since by the definition of f bar, it's strictly less than this. So we have 1 less than or equal to, and the rest of these guys are strict. Okay, so basically that in some sense sandwiches the truncated f bar strictly between fx minus 1 and f of x, and it also puts it, of course, between lower than f bar. So what this means then is that this degree of truncation is sufficient to describe x unambiguously, using this number of bits. Okay. Now, why is it sufficient to describe it unambiguously? Because each one of these intervals between f x minus 1 and f of x are unique, and this is a value that lies strictly between the two. And since the intervals don't overlap, it's unique. Now the question is it prefix free? And that's what we care about. So let's talk a little bit more about these intervals and consider these half-open intervals. And so let's start the half-open interval with 0 point this binary expansion, which is z1 through zl, which basically is f bar of x truncated to L bits. And then let's add on another 1 over 2L, and it's the open interval on the right side, and closed interval on the left side. So another way of looking at this is that it's basically on the left, it's z1 through zl, and here it's z1 through, and it's another typo here, z1, this should be through zl here. I don't know how many typos I fixed. I always find more typos. So z1 through zl, on the right it's z1 through l plus this interval, or this value, which is 2 to the negative l. So this interval then has length 2 to the negative l, and corresponds to all binary numbers that start with this string. This is the prefix. Every binary number that starts with that string that lies within that interval, because as soon as if we were to close this guy, then we would include something which adds this 1 to that last z, which wouldn't start with that string here. So that z would be incremented, and if that z was, say, 1, then it would, propagate down this way. But that doesn't happen. Carry, I guess, is the right phrase to use. So we're not including the carry in this case when we add that, so because we're keeping it an open interval on the right. And so we get then this picture that looks like this. So here we have f of x minus 1. Here we have f of x. The possible values, the open interval that I just talked about was this guy. It's closed here, the half-open interval, and it's open here, which is this half-open interval, because it's closed starting at this value, truncated f bar of x. And this interval here, this one, I should say, corresponds to the possible values of the truncation. So when we truncate f bar to f bar of x to L bits, I mean, it's possible that it would be exactly equal, that it wouldn't change. I mean, what if f bar of x was already contained in that many bits, in which case it would be there. But when we truncated to L bits, we said we had this strict inequality which said that it was strictly greater f bar of x is strictly truncated f bar of x is strictly greater than f of x minus 1. So therefore, this interval here, the one I just erased, and I'm going to write back again, this interval is half open, but is open on the left and closed on the right. Okay? Hopefully that picture makes sense. So what this means then is that, just writing it in equations, is that the truncated f bar lives in this half open interval. It's open on the left and closed on the right. We do have that 2 to the negative L is less than or equal to px over 2. And we also have this sandwich bound. So what this means is the following. This guy here, 2 to the negative L, can't be greater than p halves over 2. Right? He's half open interval on the right. The biggest possible value of him would be f bar. We're opening interval on the right, so the farthest to the right this guy could be would be here, which is open, which is the start of the next guy over here, starting with f of x. And so, since the truncated version of f bar is at most f, and is at least, in fact it's strictly greater than fx minus 1, these half-open intervals here can never be less than this, and can never sort of touch this point. So it could touch, it can't, and actually it can't touch this point either, because this is, the possible values of a truncation are open on the left. So we're sort of open on the left, thanks to the truncation being open on the left, and we're open on the right because of, everything's sort of covered up, but we're open on the right because of this bit here. So the closest thing that could be is there, the closest thing this could be is here. And so therefore we'll never ever, these values, these numbers that begin with this string, z1 through zl, can never lie outside of that interval. And so therefore that interval constitutes sort of a unique partitioning. It's a partitioning of the unit interval from 0 to 1. And so therefore any code word, if we use the code word corresponding to this truncation, that cannot be a prefix of any other code word, because any other code word wouldn't start with that string of truncated f bar of L. I hope that makes sense, and maybe if you pause this at this moment and rewind it or something, that this will actually make sense. So the point of this is the bottom line is that if this was a prefix of another code word, then we would have interval overlap. So since we don't have interval overlap, and since, because we're open on the left, open on the right, nothing can be a prefix of everything else, and so therefore the truncated version of f bar x can act as a instantaneous code for this. So okay, so let's find out what the expected length is. So we compute the expected length, which is p of x and L of x, and summed over x. And we just plug in the value of L of x, and we get the entropy plus 2 as an upper bound. And so here's an example. Now, I'm not saying this is good. Like we've done before, we've got entropy plus 1. The point of this exercise, and the main point of this, and the reason to understand this, is because, again, of what we're going to be talking about with respect to arithmetic coding. And that's going to be a bit more complicated, so it's really important to understand this first. Arithmetic coding is actually something that you really do want to know. And so therefore, you also want to know this. So here's an example for a dyadic distribution. The symbols are here. Here are the corresponding probabilities. Here's f of x. Here's the truncated version of f of x. Sorry, here's f bar, I mean. Here's f bar in binary. And here's the lengths, according to this Shannon code. And here are the corresponding code words. Okay, this is a dyadic distribution. The expected length is 2.75 bits. The entropy is 1.75 bits. The efficiency is not that good. The Huffman, on the other hand, in this particular case, using this is the Huffman tree where we first merged 3, 4, and then we merged the result of merging 3, 4 with 1, and then we merged the result of that with 2. That gets an expected length of 1.75, which is the same as the entropy. So obviously we're not doing anywhere close as good as Huffman. but this is a dyadic distribution, but again, this explains the concept. Here's another example of a non-dyadic distribution, and this is a standard notation where 0, 1 with a bar over it means that it's 0.010101 repeated forever. So here's our code symbols, the probabilities, non-dyadic. Here's f bar. Here's the binary version of f bar, and then here are the resulting code words truncated to these lengths. So it has to be prefix free. Let's verify, and indeed it is. It's nobody's a prefix of anybody else. And let's look at its expected length. It's not optimal. Entropy is 2.285. Expected length is 3.5. Huffman is 2.3, which doesn't achieve the entropy again because it's non-dyadic. But again, the point of this is to understand the idea of using these binary values, these binary expansions, as the code word, in particular truncated versions of the binary value. Now the other thing to note, sometimes, on any particular code word, it's funny because at this point in the class I would ask for questions and I would pause. And I'm not doing that now because there's nobody here. So the beauty of watching this on video is that you can pause at any time and ask yourself questions and make sure that what I'm saying makes at least some degree of sense. And so I hope, again, that these YouTube videos are of some use to you guys. And in particular this case, when I'm actually not there, it's somewhat critical and essential. Okay, so now getting to this point, on a particular code word, sometimes the Shannon length is actually better than the Huffman length, and sometimes not. And the Huffman length is always, of course, on average better. But what we're going to next do is let's study a couple of questions about, the probability of a particular code word being longer or shorter for a particular symbol, either for the Shannon length or some other code. So the question is sort of like the competitive optimality of Shannon. And we do this for Shannon because it's sort of easy to analyze. Huffman lengths, which are defined algorithmically, are much more difficult. And so let's say that L of x is the code word length of a Shannon code, and let's say that L prime of x is the code word length of any other uniquely decodable code, including the optimal ones or anything else. So we're going to prove a bound associated with Shannon and anything else that's uniquely decodable, which includes things that potentially could be much better than that. And what we have is this theorem that says that the probability, first of all, where's the random variable coming from? So the random variable is x, capital X here. So it's a function of a random variable, and the function of the random variable is this indicator, which says that L of x is greater than or equal to L prime of x plus c, and it's the probability of that indicator being 1. This event, I should say, really, this event of, if that's not clear, let's zoom in a little bit on this. It's the probability of the event. This is a little bit thick. Let's get this a little bit thinner. It's the probability of this event. Okay, the event that L of x is greater than or equal to L prime of x plus c, where x is the random variable. Okay, and that we're saying is decreases exponentially in c, which is the degree to which L of x is worse than any other code. So c is some non-negative value. Actually, it has to be greater than 1, otherwise it doesn't. Obviously, it doesn't make sense in that case. So how do we do this? How do we prove this? Well, here's the probability, and this is where you're going to see where the capital X's come in. So this is another way of writing it, just using the definitions. And here's yet another way of writing it. And okay, right. So the actually the system I was just using just crashed. I don't know if you're going to detect the delay or not in what I'm about to say. But in any event, I wanted to mention that the reason for this is that there's this -1. So it's the usual thing of ceil of A is going to be less than or equal to A plus 1. Okay, so that's where we get that last bit from. Now, this can be represented by solving for p of x and putting everything else up in the exponent of 2. And now here's where we actually solve we see how x is a random variable. So basically it's all x's whose probability is less than this value, and we're summing up p of x. And so that's in some sense what this means. If you weren't sure what this means up until now, this is the equality that you should look at, you should study and consider when you're trying to figure out what this guy meant. Okay, now I'm going to assume that that makes sense, and since for all guys that we're summing in this sum, this value on the right is greater than the probability, we can go ahead and just plug that value in up there, and then we're going to get an upper bound. Okay, and now we've sort of again divorced this. We can factor that out of the summation, and we just have a counting, which is basically further upper bounded by the summing over all of x rather than just some of the x's. And we're just now writing this thing here in this way. And this whole thing is going to be, this is the 2 to the negative c minus 1 is a constant, and we're summing x over 2 to the negative lx, and we're assuming that it's uniquely decodable, and so therefore this is going to be less than or equal to 1, and so we get the whole thing, which is less than 2 to the negative c minus 1, which is where we get the result of the theorem. So the whole exponential decay in c. So we're essentially done. Now, that essentially means that on the one hand, while Shannon isn't optimal, it's not so bad in the sense that it's highly unlikely that for a given random variable that Shannon code is going to have a much bigger code word length than any other code that's uniquely decodable. But the other thing we'd like to do is look at and see how often is it that Shannon lengths are shorter than others, or at least how probable is it? So what we'd like ideally, again, if L is the Shannon length, we'd like that the Shannon length to be shorter than any other thing than vice versa. Okay, for any other prefix code, where again L prime is any other prefix code, and can this be true for all distributions? The question is, and of course it can't be, because Shannon is not optimal, and in fact Huffman is going to be better, but still we're approximately optimal for dyadic distributions, in which case 1 over p of x is an integer, and so maybe it's actually not as bad as it looks. And in fact what we end up getting is that if we have a dyadic distribution, which maybe you don't care about dyadic distributions because you might say they're not realistic, that's not something that would ever happen, but in any event, that basically means that the length L of x is equal to 1 over p of x, which is an integer, and L prime is the length of any other prefix code. Then what we can show is that the probability of, this is again a random variable or a random event, because x is a random variable, capital X, the probability that L is less than L prime is greater than the probability if L is greater than L prime. So it's more probable to be shorter than it is to be longer. And it's only equal if for all x the two lengths are the same. Now again, this is a dyadic distribution, so before you get your hopes up about Shannon lengths, this is a very special case. So the way we prove this is by defining the sine function. This function kind of looks like this. It's sort of -1 for a while, and it's open here, it's closed, and it's open at +1. This is +1 here, and this is -1 there. And in such case, if we look at 2 to the t minus 1, then the sine function is always going to be less than 2 to the t minus 1. Why is that? Well, 2 to the 0 minus 1, 2 to the 0 is going to be 1, minus 1 is 0, right? And then 2 to the plus 1 or minus 1. So if we go out to, where's my little ink here? So if this is, say, value 1, so 2 to the 1 is 1. 2 to the 1 is 2. Minus 1 is going to be this value here. And 2 to the -1. So basically what's going to happen is at these integer points, we're sort of like this, right? And so at these integer points, obviously the 2 to the t minus 1 is going to go exponentially, and then again at these integer points, 0 included, this is going to asymptote here to -1. So what this then gives then is the following. We can actually then we're going to bound the difference in these two probabilities and show that they are greater than 0. And here's writing the actual expression for them. Here are the sum over all x such that the length of L prime is less than the length of x. And this is the sum over all x such that the length of L prime is greater than L of x. And this can be represented as the sum of just the sign difference between these two things. Right? Because once we sum over these things, if it's one sign, then we're going to get one, we're going to subtract the probability, because these guys are sort of exclusive events. This is exclusive with this, right? And so we can sum over all of them, and then the sign resolves the exclusivity by essentially depending on whether or not L of x minus L of x prime is -1, 0, or 1. And so this is then just the expected value of the sign. And if in keeping with my notation, I should officially write these as capital X here, not lowercase x, because these are now random variables. So officially that's a typo. And then we can take essentially this bound that we derived here, and it's the sum over x, p of x. It's 2 to the t minus 1. This is going to be 2 to this difference. This is the difference up here. It's 2 to the difference minus 1, which comes from up here. Okay? Summed over all of x, and then we're using the upper bound here. This upper bound and this upper bound are the same. Okay? Pretty good. Now we're going to use the dyadicity of the probability distribution. And so this is going to allow us to write the probability as 2 to the negative L of x. And that's going to do some nice canceling, as you can imagine. And we can write it in this way, where we get this difference. This basically, these are the probability distributions, and we're summing over all of x, so that whole thing is going to equal to 1, since that's all of the probabilities, that corresponds to all the probabilities. And then, as you can well imagine, Kraft's inequality is going to come into play here. And we can upper bound this other one by exactly 1. So this one is exactly equal to 1. This one we can upper bound by 1. And so we get less than or equal to 1 minus 1, which is, of course, equal to 0, which is what we wanted. Okay. So, therefore, we've got this nice thing that shows that it's more likely than not, in the dyadic case, to have a short code word than a longer code word than any other, for using the Shannon lengths. The Shannon lengths are more likely to be shorter than longer under the dyadic distribution. So Shannon and dyadic looks pretty good. Okay, so that's the end of Shannon, Fano, and Elias coding. Again, like I said, these concepts will become very, very useful in the case of arithmetic coding. Please review them. This is the last topic that's going to be on the midterm. If you have any questions about these lectures or anything, so I'm posting these videos on the discussion area. You can post questions there. On Tuesday, what we're going to do is play games, and this is where we're going to have a little bit of fun. We're going to look at Shannon games and stream codes. So here's the games and here's the stream codes, and the question is, what do games and stream codes have to do with each other? We will find out. Come to tomorrow's lecture. We'll also do, well, tomorrow being Tuesday, today is Monday, we will also have a midterm review. Hopefully some of you will actually watch this video, maybe even Monday night, tonight. I will post a email for everybody to that, so that you should watch it as soon as I post it, which I'm about to do right now.